I'm Pete Zelinski.
I'm Stephanie Hendrixson.
At the most recent International Manufacturing Technology Show, we saw something we want to share with you. It's a 3D printed space habitat, like lunar habitat, and it says a lot about large format 3D printing.
The demonstrator that we saw at IMTS in the Emerging Technology Center is a scaled-down version of a lunar habitat that was designed to be shipped to space on a SpaceX Starship.
Space Habitat. So this project was a collaboration involving Saga space architects in Denmark and a Swiss boarding school, the Rosenberg Institut. The habitat structure was 3D printed by Ingersoll Machine Tools, maker of really big machines, including really big 3D printing systems. We learned about this work from Chris Chaya, who's a lead process engineer with Ingersoll.
Yeah, so maybe the first thing that we learned out of that conversation was that the demonstrator we saw at IMTS was actually printed in the wrong direction. So it's a scaled down version. It was only 9 feet tall. 9 feet is about the max size that the Ingersoll printer can do, like a 0-degree wall. So they just printed it straight up in one go. They did later have to cut it into pieces to ship it to IMTS, but it was made in one piece. The actual Rosenberg lunar habitat, the full-scale one, is 23 feet tall, and it's printed in 6 sections, each of which is that full 23-foot height, but it's printed laying on its side. And so when you look at the finished product, the layer lines are going up and down instead of back and forth. But in both cases, both habitats were printed from the same material. It's a glass-reinforced ABS that has a special UV-resistant additive in it.
The actual habitat sections were printed, 6 different sections for the complete habitat, each one printed to the height of the dwelling itself. So that means the length of each of these sections in the machine is the height of the habitat, 23 feet. And the challenge with a 3D printed polymer structure that big is preventing it from cooling too quickly. If any part of the layer solidifies too much, gets too cool, then it impedes bonding with the next layer. So you got to get all that material down there quickly enough, all in one layer. Side note, a way that Ingersoll often deals with this is by slicing very long builds like this at 45-degree angles, like 45-degree ramp slices. Printing that way creates a smaller layer area that needs to be printed with each layer and helps them control that cooling time. Not an option in this case. So how do you get that layer down quickly enough that this cooling time is not an issue? So we talked a little bit about that with Chris Chaya from Ingersoll, and what he explained is that Ingersoll's understanding of the servo control of a large machine was part of the solution. Ingersoll Machine Tool makes large, precise metal cutting machine tools, very big machines with fine precision. That same level of precision was not needed in this case, like precision measured, accuracies measured in thousandths of an inch, and that gave Ingersoll some room to tune the servo control to allow for very rapid deposition of this polymer material on this really, really big 3D printer.
Yeah, I think a big takeaway from that conversation for me was that the size you can print is not just limited by the size of the machine. You also have to be thinking about the cooling rate of the material and the motion of the machine. But I want to say a little bit about why 3D printing was important for this habitat project. The design choices that they made 3D printing the best way to build this lunar habitat. So if you look at sort of the shape of the structure, it's got this sort of like rounded triangle geometry to it. And they chose that because they could fit 6 of them inside the round payload of the Starship. And so that shape helps pack more of these habitats in, but also allows for more living space once the habitat would actually be on the moon and in use. So that's a difficult shape to build with other processes. The other thing is if you look at the outside surface of these panels, they've got this like weird topography going on. They were actually topology optimized. So they've been designed to withstand the pressures and the gravity and the conditions that they might have to withstand in use on the moon's surface.
So that outer form of the habitat, it's not just about sort of the interesting, pleasing aesthetics of it, it's performing a vital function of structurally containing that pressurized atmosphere it needs to hold. But the aesthetics are not unimportant. This needs to be an appealing place to live. The idea of the habitat is that astronauts would live here for an extended period of time. It's a little house. 2.5 stories. There is a working level, there is a level of living space, and then another half level up top where the sleeping quarters are. So this application, 3D printing an entire tiny house, might seem like a strange additive manufacturing application, but it wasn't all that long ago that 3D printing really large tools also seemed like an odd way to use 3D printing. And now it is an accepted, proven application of large format additive manufacturing. The Ingersoll team had a lot of fun with this project, thinking their way through it, delivering these habitat structures, because it fits into this larger context of how large format additive manufacturing is still discovering its use cases.
If you want to learn more about the Rosenberg Lunar Habitat, Ingersoll, or anything that we've talked about, we'll put links in the show description. And if you're interested in more on large format printing, check out our channel, Additive Manufacturing Media. We have a couple of episodes of our series, The Cool Part Show, that look at large format 3D printing, as well as some other videos. Thanks for watching.